All right, I guess we can start. It's a great pleasure to host David Held from Carnegie Mellon University. Dave is an assistant professor at the Robotics Institute. He directs very successful robotics lab, focuses on perceptual robot learning. His research is in the intersection of robot perception and planning with a focus on manipulation and automated driving. Dave is the recipient of NSF Career Award, Google Award, probably some other awards. So we're very happy to have you here today, and we're looking forward to your talk.
Great. Thank you very much. Thanks everyone for coming, especially during these very tumultuous times. I'll actually just give a shout out. Memorizing an introduction is always an impressive feat. So that was very impressive. Okay, so today I'd like to talk about my research on perceptual robot learning. So a robot consists of a perception system that takes its sensor inputs and tries to estimate the state of the environment, and a planning system that takes this estimated state and tries to predict what actions the robot should perform to achieve a given task. And we typically divide researchers in the same way. We have vision researchers that work on the perception side and robotics researchers that work on the planning side. And what I'd like to ask is, can we build a better system by thinking about these parts together, both perception and planning? Now, to clarify, I'm not talking about merging perception and planning into an end-to-end black box. I'm just talking about thinking about perception and planning together. So when I propose this idea, sometimes people ask, well, why can't roboticists just use the output of a computer vision method? And to answer that question, let's look at what computer vision methods typically produce. So here's an example output from a computer vision system, which is detecting and segmenting objects in these images. So the goal of computer vision is to understand what is in an image. On the other hand, the goal of robotics is to understand what will happen if a robot interacts with its environment. So if this robot were to interact with this crumpled towel, what would be the effect? That's what a roboticist would need to know. And so roboticists tend to have different goals from computer vision researchers. And thus, we need to develop new perception and planning methods to meet the needs of a robot system that must both perceive and act. Of course, these perception and planning methods for robotic systems can build on previous methods that were developed in isolation, but sometimes we need to develop new methods that integrate both perception and planning in new ways. And so how do we bridge a gap between perception and planning? For example, if we have this crumpled towel, how should we represent this object to enable a robot to interact with it? There's different types of representations that one might think of, and they have different trade-offs in terms of how easily we can infer them from the robot's observations or interactions with the environment, and how suitable they are for a given task. So my goal is to learn to manipulate novel, perceptually challenging, and deformable objects, and this requires rethinking robot perception and planning algorithms to handle these types of objects and manipulation tasks. So here's a few examples of what our lab has been able to achieve using this perspective of perceptual robot learning. I don't know how to get rid of the thing on top, except there's also a question in the chat. Should I be monitoring the chat?
I'll monitor the chat for you.
Okay. I don't know what just happened when I clicked on chat.
If you want to, you can move it to the.
Okay. I think we're okay. Oh, here. I see it. Great. Okay. Okay. Anyway, so here's what our lab has been able to achieve. You can see we've been working on different tasks relating to cloth manipulation, grasping transparent or reflective objects, and pouring transparent liquids into transparent cups. And today I'm going to mostly focus on the first two projects, and we'll see if we have time for one more, but we'll mostly focus on the first two. Okay, so I'll start by describing a benchmark that we developed for deformable object manipulation. This benchmark was developed by my student Xingyu Lin, who is currently looking for postdocs. So if you're looking for an excellent postdoc, look out for Xingyu. And if we think about benchmarks in computer vision has really been driven forward by these large-scale data sets, such as ImageNet or Cityscapes, that allow different researchers to run their algorithms and compare performance and see if progress is being made. In robotics, we don't really have data sets. Instead, we have the closest thing that we have to that is simulators. Here's an example of the Majoko simulator, which is used to compare performance on these locomotion tasks. People in Michigan would probably say that it's not very realistic, but it's popular in certain reinforcement learning communities to allow researchers to compare the performance of different algorithms. But what's the state of deformable object manipulation? So here's a few examples of papers in deformable object manipulation. There's been some great work in this area, but we can see that most papers evaluate on different task simulators and robot setups. And this makes it hard to compare algorithms to really see if we're making progress on these tasks. There's also wide applications of manipulation for deformable objects. Here's a few example applications. I'm sure you can think of many more. And there's many challenges in manipulating deformable objects, such as their high dimensional state representation compared to rigid objects that can be represented just by a 6D state. Deformable objects are much higher dimensional. They have fairly complex dynamics, and they have self-occlusion. So you can only see some part of this deformed cloth, but much of it is being occluded. So in order to spur research in this area and make it so that researchers can compare algorithms more easily to each other, we developed this benchmark that we call SoftGym. It's built on top of the NVIDIA Flex simulator. And we have various tasks in this benchmark that involve transporting water without spilling, pouring water into a cup, straightening a rope, folding a cloth, spreading a crumpled cloth, and dropping a cloth in the air, hopefully in a flattened way. And the community has actually already started using this benchmark. Here's two papers from groups outside of CMU that have used this benchmark for very impressive papers. So I encourage you to check it out as well if you're interested in this topic. And in addition, we also benchmarked a number of different reinforcement learning algorithms on these tasks. So here with this black line, I'm showing the performance of an oracle, which assumes access to the ground truth state and ground truth dynamics and does CEM planning. So this is, CEM planning is obviously not the best kind of planning method out there, but this still puts at least somewhat of an upper bound on how good you can expect the performance to be compared to a method that uses a similar planner and only has access to the raw observations and needs to infer the dynamics. This black line uses ground truth observation and dynamics. And here with the colored lines are the performance of different methods that use deep reinforcement learning to try to achieve these tasks. And I'm not going to go through each of these methods now. The main thing I want you to notice is that if you look at the two tasks of spread cloth and fold cloth, the performance of the best deep reinforcement learning methods are still well below that of the oracle. So there's a lot of room for improvement on these tests. Great. So that's going to inspire our work to try to improve performance on these tests as well. And one question that we wanted to ask is, why does deep reinforcement learning perform so poorly on these tests? Well, it's hard to really get a clear answer to that, but let's try to build up a little bit of intuition. So first, how do deep reinforcement learning methods work? At a very high level, they might take some observation of the environment like this, compress that observation into some latent vector representation, but then they map through a policy to predict the robot actions, or they can map that vector through latent dynamics, also take as input the robot action, and then try to predict the next state in the form of another latent vector. These methods are called model-free and model-based RL respectively. And one thing that you would ask looking at the slide is, what does this latent vector actually capture about the observation? And is this latent representation actually sufficient for my task? And it's hard, again, to really get a clear answer to this question for deep reinforcement learning methods in general. But there's one particular class of methods that we can get a little bit more intuition about, which is methods that do planning in latent space. So such methods take an observation of the environment and encode it to a latent vector. They might then take some proposed action sequence and use a latent dynamics model to simulate the effect of this action of this action sequence. So you get these lay-in predictions, which you can score with the lay-in reward function. You can do that for different possible action sequences, predict the effect of each one in lay-in space, and then pick the one that has the highest score. Now, let's see how well this method works. So here I'm showing the performance of Planet, which is at the time, it was one of the state-of-the-art methods that do planning in lay-in space. And here's the performance of Planet on the task of pouring water without spilling. And I don't know if you can see, but it's actually spilled a bunch of the water outside of the cup. Now, why does it do that? Let's see what Planet thought was going to happen using its plan in the lay-in space. So here's the reconstructed images from its lay-in plan. And you can see in its lay-in plan, it predicted that it would pour the water perfectly into the cup without spilling, whereas in reality, it did spill. And so why is this? Well, when you think about it, it's actually somewhat, it actually makes sense because it's very hard to predict exactly where these spilled droplets will be. And they also take up a very small number of pixels in the image. So the easiest thing for the lay-in model to do is pretty much to ignore these small spilled droplets, which maybe is fine for certain parts of the objective, but for our objective of pouring without spilling, it doesn't actually work very well. Here's another example of using this model for flattening a crumpled cloth, and you can see it doesn't actually do a great job. The cloth is still very crumpled, but in its prediction, it predicts just this big orange blob without any of the wrinkles in the cloth. And so this, the logic here is probably the same. The wrinkles are very hard to predict exactly where they're going to be, and they take up a very small number of pixels in the image. So the easiest thing to do is just ignore the wrinkles and predict just the overall, shape of the overall sort of area where the cloth is. And so what we see in this particular example is that compressing an entire scene or even a single complex object into a single lay-in vector can result in losing subtle but important details. Now, if you were a hardcore deep reinforcement learning person, you might push back on this and say, well, can't you use just a larger lay-in vector to scale things up? And yes, that's true. Archimedes once said, give me a lever long enough and a fulcrum on which to place it, and I shall move the world. His lesser well-known brother, R.L. Medes, once said, give me a large enough lay-in vector and enough computation, and I can memorize any training set. Both of these statements are technically true, but not terribly useful. And so yes, with a large enough lay-in vector and enough computation, we could probably get these tasks to work. But the point that I'm going to make is we'll see shortly how we can learn much more efficiently by encoding more environmental structure into the representation that is used for these tasks. Okay, so to wrap up this section, we introduced a new benchmark for deformable object manipulation known as SoftGem, which allows researchers to easily develop new methods for these tasks. We demonstrate that deformable objects present a large challenge for state-of-the-art deep reinforcement learning, and we show the downsides of lay-in vector representations for deformable objects. Are there any questions about this part before I continue? Yeah.
Yeah, so one of the limitations I see about this, I mean, I think the latent vector one is a big one, definitely, but specifying that latent reward function seems like very difficult to actually get right.
Yeah.
Especially for tasks like pouring, where most of the time you have zero reward, right? Because you haven't poured anything, and only at the last second do you get reward.
Right. Yeah. Agreed. Yeah. There's a number of difficulties. So one is that if you're operating in lay-in vectors, you have to learn a mapping from the lay-in vector to the reward, which introduces another place that your model can make mistakes. And how do you design a good reward function? Is it sparse, which makes it difficult to learn? Yeah, these are all great questions. So I guess we'll see in some of the other work that I present other kinds of reward functions. But yeah, I agree that's going to be a big challenge for these methods as well. Yeah, great. So, okay, so that benchmark inspired us to do further work and try to address this question of how should robots do cloth smoothing with a dynamics model. So, we're going to explore that in this work. And this work is led by my students Xingyu and Yufei. And again, Xingyu is looking for questions. Okay, so, okay, so how should we represent the dynamics model for this task? The first approach that is the most common that we saw before is to learn the latent vector dynamics. So you can take an observation, compress that to a latent vector, concatenate the robot action, pass that through your latent dynamics model, and try to predict the next latent vector. And what we saw is the latent vector dynamics model does not encode any environmental structure, which can make generalization to new configurations difficult. Another approach is to learn a pixel dynamics model. So given an image, you can try to predict an image of what the cloth will look like in the next time step. This approach has been explored a lot at Berkeley. For cloth, it's been tried out by Kim Goldberg's group, including Daniel, who's now doing a postdoc in my lab. And the benefit of pixel dynamics is that it actually captures the spatial structure of the environment as opposed to latent vectors. But the downside is that pixel dynamics might not sufficiently capture the underlying physics of the cloth. So the approach that we're going to propose is to learn a graph dynamics model. So given a point cloud observation of the cloth, we're going to estimate the mesh of the cloth. We're then going to use a graph neural network as our dynamics model, which will predict how this mesh will deform in the next time step after taking a robot action. So why should we use a mesh for cloth? Well, a cloth is sometimes modeled in the graphics community by a set of points connected by springs, and you can put other forces on this graph as well, such as gravity, collision forces, and friction. But there are some challenges in using a mesh representation for cloth. So the first is what we actually see is, say, an RGBD observation of the cloth, which we're going to use to extract a voxelized point cloud, but we don't get to see how these points are connected on the underlying cloth mesh. We actually don't even get to see most of the points themselves due to self-occlusion. So what we see is just the points on the visible surface of the cloth, but we don't get to see the points underneath. And so how should we handle these occlusions? Well, the best approach is probably to estimate a distribution over the full mesh configuration of the cloth, including uncertainty over the occluded regions. And this is an approach that we're actually pursuing right now in ongoing work. So stay tuned for our future publication in this area if we can get it to work. But for this project, we're going to make just a we're going to make just this point, which is that a graph dynamics model combined with a very simple approach for handling occlusions can significantly outperform using pixel dynamics or latent vector dynamics or model-free policy. So what is this simple approach for occlusions? It's the following. We're going to learn to estimate how the visible points on this cloth are connected. So in this cloth image here, you can see that these pairs of points connected in green are directly connected on the underlying cloth mesh, whereas this pair of points connected in red are not directly connected. They're just near each other because of how the cloth is folded. Can everyone sort of see that on the slide, or at least imagine what it might be referring to if you can't see it? Yeah, okay, there's at least some nods. So, okay, so we can see how these visible points are connected. We can then create a graph based on the estimated connectivity of the visible points. Here's a cartoon illustration of what that might look like. We call this a visible connectivity graph because it's a graph just over the visible points. And then we're going to learn the dynamics model over this graph of visible points. We call this visible connectivity dynamics. And this dynamics must learn implicitly to take into account the partial observability of the cloth. So how does this dynamics model work? So we're going to take as input an observation of the cloth, which we convert to a voxelized point cloud. We then will start by connecting all nearby points by edges. Then we'll use an edge prediction graph neural network to predict which subset of these edges are directly connected on the underlying cloth mesh and which are not. We'll then take this estimated mesh and input that to the dynamics graph neural network, which will predict how the mesh will deform in response to the robot action in the next time step. We can then input this estimated mesh back into our model and continue to perform to predict the effect of a sequence of actions. Okay, so how does the edge prediction graph neural network work? So we're going to take as input this graph in which we've connected all nearby points by edges. And then we're going to do the typical graph neural network operations, which is we encode each node and edge as a latent vector, perform message passing between the nodes and edges, decode each edge, and the output is going to be a binary prediction on each edge of whether that edge is an edge on the underlying cloth mesh. So the output is just a value between 0 and 1 on each edge, which is our prediction of whether that edge is actually an edge on the underlying cloth mesh, or whether it's just connecting two nodes that happen to be near each other because of how the cloth is folded. Does that part make sense to everyone? Okay, yep.
Yeah, I don't quite get it. I mean, it seems like when you have that cartoon, the reason that you would prune out an edge is that visually you could see that there was like some break between the things or something.
Yeah.
But this doesn't seem to take in the actual image. It just has a mesh. So how could it possibly?
So the input is basically a mesh which has the XYZ position of each point. And so it can kind of use depth discontinuities and changes in sort of the smoothness in certain regions to figure out where the breaks might be. So yeah, I agree that it's a difficult task. We don't do perfectly on this task, but in our experiments, we do well enough to have a reasonable dynamics model.
And how do you train this?
We train it in simulation. So in simulation, we have ground truth for these kinds of edges. Yeah, and then we transfer to the real world. Okay, so that's the edge prediction GNN. Great questions. So next, we're going to use this prediction in our dynamics model. So we're going to take as input both the initial graph in which we've connected all nearby points by edges, as well as this graph in which we've estimated the mesh edges of which points are actually connected on the underlying mesh. And we're going to input both of these kinds of edges into our dynamics GNN along with the robot action. The dynamics GNN will work in the same basic way. We encode all the nodes and edges, pass messages between them, and then decode them. And in this case, the output is going to be the predicted acceleration on each node of how that node is going to move in response to the robot actions. Okay, so that's our model. How do we use it for planning? So in this paper, we focus mostly on the smoothing task, although we show that it could also be used for other tasks as well, like folding if you change the reward function. But for the smoothing task, the reward function that we're going to use is the following. So we're going to take the predicted position of all of the nodes in our graph. We're going to surround each node with a sphere, project these spheres onto a plane, and then compute the total area of these projected spheres, and that will be our reward. So the greater area that's covered, the more smooth or spread out the cloth is predicted to be. Okay, and we're going to use an extremely simple method for planning here, which is simple random shooting. So we're going to basically pick n random pick and place actions. We will simulate the effect of each one using our mesh dynamics model, and then we'll score each action according to the predicted reward. And then we choose the action with the highest predicted reward. So this is one of the simplest planning methods. Dimitri has worked on much more complex planning methods that I'm sure would improve the performance of our method. But as a reminder, the point of this project is just that using a graph dynamics combined with a very simple approach for occlusions, as well as a very simple approach for planning, can significantly outperform using a pixel dynamics model or a latent dynamics model or a model-free policy. Okay, so we're going to train this. We train this method in simulation using SoftGem, which we showed earlier. We train it with 2,000 random pick and place actions. In contrast, the baselines are all trained on over 100,000 pick and place actions, which is the number that they were trained on in their original papers. And we use a voxelized point cloud as input to the graph dynamics model, which allows us to easily transfer from simulation to the real world because we voxelize the point cloud in the same way in sim and real. And so the input to our method looks similar in both cases. We're going to train one graph dynamics model, so just one set of weights in simulation, and we're going to evaluate it on these three different types of cloth: a cotton square cloth, a silk square cloth, and a cotton t-shirt. And here you can see the performance of our method. So on the left, you can see the pick and place actions that a robot is performing to try to flatten this cloth. On the bottom right, you can see our predictions. You can see our predicted mesh and how this mesh is predicted to change in response to the robot actions. And on the top right, you can see the different, some of the different actions that we are evaluating. And the color indicates how good we think that action is. So green is an action that we think is really good, and red is an action that we think will not work as well. The arrow shows the pick point and the place point. And you can see that for each of these different types of cloth, we're able to do a pretty decent job of flattening the clothing.
Good.
Yeah.
So, of course, RL, very popular. Have you tried just really simple benchmarks, just like, you know, pick a point on the edge and pull it, like stuff like that?
Yeah, so we did not ourselves, but one of the papers that we compare against from Berkeley did compare to benchmarks like that and showed that they outperformed those kind of heuristics, and we outperformed the Berkeley paper. So I guess it's not the same, you know, exact environment, but that's the argument that we were making.
Right.
We do actually want to follow up with the journal paper where we directly compared to more comprehensive set of baselines, but yeah, that was our argument for that.
Yeah, it's just, I mean, I think the approach is really cool. I just wonder how necessary is it to build this mesh, right? And do all this very intensive processing for a task like this. It
Yeah.
seems much simpler.
So that's a great question. Okay, so besides the answer that I just gave about the Berkeley paper having compared to those baselines, another answer that I can give is we're learning a graph dynamics model. We're learning a dynamics model, and a dynamics model can be used for different tasks. So maybe for a cloth smoothing task, there might be other ways to get it done. So there's also a nice paper by Sharon Song where she picks up the cloth and just flings it. Okay, but we're hoping to use a dynamics model for lots of different tasks, like hanging up a cloth on a hanger, or hanging over a rod, or cleaning a surface, or there's lots of things you can do with a cloth besides smoothing, and the dynamics model could theoretically be used for this different tasks as well, if with the right reward function. Does that answer your question?
It does. I'm not sure how generalized the dynamics model will be across, like how effective a single model will be across all those tasks. Because as I see it, we often change our representation of something depending on what we're doing.
Yeah, I agree. Yeah, actually, another direction that we're currently working is on sort of multi-scale dynamics models. Another downside of this approach is that it's relatively slow. So I think it takes about 15 seconds to plan each pick and place action, which is not terrible, but we would like it to be faster. So maybe we can use sort of a coarse model to get an initial plan, and then refine it with this particle-based dynamics model. And it's also possible that for different tasks, you might need different models. I guess our hope is that by representing the cloth at the finest level of detail that we could think of, which is at the level of individual particles in the cloth, that would be at least capable of learning a generic dynamics model. But I also agree that it depends on what data it's trained on. So I mentioned this one was trained on just random pick and place actions, which maybe is good enough to cover the set of actions that you might need for a smoothing task, but probably wouldn't cover all the actions you would need for hanging it on a hanger. So you would need some additional data to train the model for that. So I agree, both in terms of data and representations, there's more to explore here. Yeah. Yeah.
There are an awful lot of robot motions involved in pulling the shirt. Have you thought of using like a mechanical framework that you can stretch the cloth over and just
Yeah, you can buy things like that. There's other companies developing machines that are dedicated to the task of say folding a cloth. Usually you have to like flatten the cloth and feed it in a flattened form, and then it kind of folds over a few ways. So yeah, I guess our idea here is to try to develop a method that can be used for many different tasks. So here we're demonstrating it just on this one task of smoothing a crumpled piece of clothing, but we're hoping that a graph itself, I think, is a pretty generic representation, and we're hoping to later demonstrate on other tasks as well. Yeah, great questions. Dimitri, do you have a follow-up, or I don't know if you did?
Well, I mean, it's just a minor point. You're like, well, we're going to model it at the finest level of detail. No, but aren't we back to Archimedes then, right? Like, give me a perfectly modeled cloth with infinite detail, and I can do anything, right? I mean, it seems like we're back to that.
Yeah, I mean, I guess here I'm showing like a practical implementation. In this particular case, we're not actually modeling the occlusions perfectly, or really almost at all. So some follow-up work will have to figure out how should you model occlusions. And of course, yes, modeling the full configuration of the cloth in terms of its full distribution and all of the different ways that it could be crumpled to explain the occluded regions is probably too much. I mean, POM DPs in general are known to be intractable. So we're going to have to make some approximations to handle the partial observability. So this is really just a step in exploring this more general direction.
But I guess what I heard was that you want to make inferences about the properties of the thing that you're taking action on,
Right.
not the actions itself, right? And that is the distinction. Is that a correct way to think about it?
Yeah. So in all of these, in all the projects I'm going to present, we take sort of a very object-centric way of trying to figure out how the object will change when a certain action is applied. In this case, the action is sort of imagining a point on the cloth is moved in some direction by a robot, and then the rest of the cloth deforms in response to that.
I will just foreshadow. There was a Nerf question coming from me, so I'll save it for the end.
Okay. Okay. So let's see. So yeah, great question. So here's some more visualizations of us folding 24 different examples of cloth configurations. So this is the same 3 types of cloth we showed before, each one in 8 different configurations. And you can see that we're able to blend all of them. Okay, so how do we compare the different baseline approaches? So here what I'm showing is the performance of, I'm going to show the performance of different methods on the task of flattening a square cloth. The x-axis is number of pick and place actions that each method is allowed to perform, and the y-axis is the normalized improvement. So 0 is no change from the initial state, 1 is perfectly flattened. Here you can see the performance of a model-free policy. Here's a performance of a latent vector dynamics model. This is the performance of a pixel dynamics model. And here's a performance of our approach. And you can see that we are able to much more quickly flatten this cloth. Now, all of these methods were trained on the square cloth and tested on the square cloth. But here you can see what happens if you train on a square cloth and test it on a rectangular cloth, or if you test it on a t-shirt. And you can see that our method is able to generalize pretty well to these other types of cloth shapes that it was not trained on, compared to the baseline that does not generalize very well. So this also partially answers your question about Archimedes. That, I mean, one nice thing with our approach is we're at least able to show generalization to different cloth shapes that we haven't trained on, like a t-shirt. I'm not saying you can generalize to everything, but at least shows some level of generalization much more than the previous approaches. Okay, so to wrap up this section, we're learning a visible connectivity dynamics over the visible part of the cloth. Our mesh-based dynamics model better models the cloth physics compared to previous approaches, and we demonstrate zero-shot sim material transfer for cloth smoothing of different materials. Okay, so maybe I'll take your next question now. So, yes,
So you're trying to model effectively the appearance of the object as, as essentially discontinuities that, that's the dynamics. But,
Right.
but we have all these fabulous NERF models that are coming up that are able to predict, they're able to provide parameters over the appearance of objects in different spaces. Why would I long-term take the object dynamics approach as opposed to trying to model versus a NERF?
Right, great question. So I guess right now our assessment is that NERF is good at representing the 3D shape of an object, but not necessarily the dynamics, or in particular, in our case, the connectivity of the shape. So what we really want to know is which points are connected to which other points, which will help us predict how the cloth will move if you pull on it. NERF is mostly will give you the 3D shape, which we actually can already kind of observe with our 3D sensor. But I mean, maybe you can give other parts of the 3D shape as well, but not necessarily the connectivity. So that's the part that I think where a mesh can really shine. It explicitly represents connectivity through the edges. But yeah, I think there could be more to explore there in terms of combinations. Yeah, great question.
Quick question on the connectivity. So one problem with graph neural networks is when the density of point cloud is sparse relative to the training set in practice, which can happen in moving robots, mobile robots.
Okay.
That affects the performance. I wonder if you have any insight to share on that and the generalizability of this approach for mobile robots.
Okay. Yeah, that's a good question. So, yeah, in our case, it's a tabletop manipulation task, and we have reasonably dense observations from sim and real. And so we actually sparsify the observations by fitting a voxelized point cloud to it, and we keep only 1 point per voxel. And that allows us to ensure that it looks the same between sim and real. With mobile robots, you often have the opposite problem where it's too sparse, like you said. And so we have some work in our lab on shape completion. So given a partial observation of an object from one perspective, we learn to complete the shape from the other perspectives. So I guess that's probably the first thing I would think to try is if you have a sparse point cloud, maybe you can try to densify it and then learn a model over your predicted dense point cloud. Yeah, I'd have to think more about the particular application that we're talking about. So here we do some ablations. So the left is showing our full system. On the far right, we're showing what happens if we don't try to estimate the mesh. We just connect all points that are near to each other with an edge. It still works reasonably. There's a little bit of a drop in performance compared to our full method. So there is some benefit, but yes, using a graph itself, even without anything else, still actually does decently on this task. So you're right, a lot of the benefit is just using the graph. The middle bar is showing what happens if you take your estimated mesh, and instead of learning a dynamics model, we put the estimated mesh into our flex simulator. And there's a drop in performance there as well. And we've spent some time trying to fix this because in theory, you might think, why learn dynamics if you already have a simulator that can simulate graphs? And we weren't able to get the performance up to the same level as using learn dynamics. Both for this project as well as for our ongoing project. And so we have some speculation about why that is. I think my main theory at the moment is that the predicted mesh is not going to be perfectly accurate. We're voxelizing the point clouds, so we're not putting the mesh nodes in exactly the right space, and then we're connecting them by edges, but our edge prediction is not exactly right. And so the physics-based simulator is assuming that we have sort of perfect perception. You know exactly where the nodes and edges are and modeling physics on top of that. Whereas our learned dynamics model is kind of learning with inputs that are imperfect. And so it's learning to handle imperfect perception. So we believe that's the reason why we do better than using a simulator. But we haven't conclusively ruled out all other possibilities yet. That's our theory. Cool. Yeah.
I guess one nice thing about images is you have the scene in the image.
You have the what?
You have the scene, right? Yeah, you have the environment is in the image as well.
The scene. Yeah.
So in principle, like for your coat hanging or different objects, like you might be able to train and try and attempt those. It probably won't work that well. So I just wondered, in your method, you mentioned like a general dynamics models for different tasks. Do you not have an intuition about how you'd be able to incorporate the environment and learn a dynamics model for different kind of contact events?
Yeah, that's a great question. We'll probably start off with something easy, like imagine a rigid rod or hanger. And then you don't have to model the dynamics of that object. You just have to model the interaction between the cloth and that object. I guess there's some similar examples with graph neural networks that show that they can model interactions between rigid and non-rigid objects like liquid, or we have the table. More difficult would be if it was an actual hanger that can kind of move on the rod. Yeah, I guess, yeah, there are definitely going to be interesting challenges ahead of modeling the interaction between these different types of material. So next, I'm going to try to talk about my next project, which is about bimanual goal condition cloth flattening. And the task here is we're going to define a folding task by a series of sub-goals that we're going to input to our method. And then we want to learn goal condition policy. It takes us to input the current observation and the sub-goal and predicts the actions that the robot will take. We then want to have a policy that also is going to decide whether to use a bimanual or a single arm action for manipulation, depending on the task. So how are we going to do this? So the standard DeepRL approach would be to take as input the observation and goal and train a policy end-to-end to output robot actions. However, this doesn't quite work as well as we might like, because it jointly reasons about the relationship between observation and the goal and how the robot needs to move to achieve that goal. An approach that's a little bit better is to instead output pick and place points. And this works better, but it still needs to jointly reason about the relationship between the observation and the goal and where the robot needs to grasp the cloth to achieve that goal. So our main insight is that we should separate out the desired object motion from how the robot is going to take actions to achieve that goal. And we're going to do that through this intermediate representation, which is our prediction of the correspondence between the observation and the goal. Okay, so let's dig into how this works. So the first step is we're going to try to estimate the correspondence between the observation and the goal. So if this were our observation and this were our goal, then for every point in the observation, we wanted to predict where did that point move to in the goal. We're going to, again, take as input sub-goals. So these observations and goals are just one action apart. And so each point has moved via that action to some location in the goal. We're going to use a simulator to find the ground truth correspondences between the observation and the goal. And we'll represent those correspondences as an image like the one you see on the right with vectors showing the movement between the observation and the goal. So then we're going to input the observation and goal into a flow network that is going to estimate these correspondences. The flow network is a similar kind that you might find in optical flow methods that are typically used for video processing to predict where each point has moved from one frame to the next. And we'll train that in simulation using geometry. Okay, so our method takes input the observation and goal into this flow net that outputs a flow image showing the correspondences between the observation and the goal. We then input this flow image into a pick net that's going to predict which points the robot should grasp to pick the cloth. And then we will query the flow at the pick points to find the place points. points. So let's talk about that in more detail. So here's the observation, the goal. Suppose this is our estimated flow. And now we've predicted, suppose these 2 points to be the points that the robot will pick. We'll then just query the flow. So we'll look at the flow vectors and find the endpoints of those flow vectors. And those are the predicted place points. Okay, so that's how we get the place points. We can also, here's how we switch between single arm and dual arm actions. So suppose that these are the estimated flow vectors, and here are the pick points. If the pick points are within a given threshold, then we can just merge them into a single pick, into a single action. Okay, here's another question that we look at. How do we decide when to progress to the next subgoal? So in this case, we're going to use flow as well. So we can take the flow and compute the flow between the current observation and the current subgoal. And when we'll progress to the next subgoal when the average flow magnitude to the current subgoal is less than a given threshold. That tells us that our current configuration is sufficiently close to the current subgoal, and now it's time to move to the next subgoal. So we're going to train this in SoftGym as before with 20,000 random pick and place actions and transfer it to the real world. And in this case, we're using depth images as input. So again, sim-to-real transfer is relatively easy compared to other methods that might use images. So to kind of reiterate the main point here, as opposed to previous work that directly outputs robot actions or pick and place points, we're going to separate out. First, we infer the desired object motion in the form of this flow image of correspondences, and then we will infer the desired robot actions. So separating out the reasoning about object motion and robot actions. Also as a review, our method takes advantage of flow estimation in 3 ways. The first is explicitly reasoning about the relationship between the observation and the goal. The next is determining the place points by querying the flow at the pick points. And the third is using the flow magnitude to decide when to progress to the next subgoal. Okay, so how well does our method work? Here you can see some videos. So the goal that we're trying to achieve is shown on the top left, although its input to our method again is a series of subgoals. And you can see that our method is able to figure out what actions it takes to achieve that goal. And in this case, it's figured out, it's using bimanual manipulation, and some of the other cases we saw, it was using single arm manipulation.
Wait, how many subgoals are there? Are they hand designed?
Yes, hand designed. Yeah, and it depends on the task. Each task we define subgoals.
Like average.
So I mean, so here are the different goals on the first row. So so it just depends how many actions it would take to achieve the task. So if you're folding over 4 corners, there are 4 subgoals. Yeah. Okay, so the top row is the goals. The second row is what was achieved by our robot, and we train this in simulation on a square cloth. But here you can see us executing it in the real world on a rectangular cloth. This is white, but white doesn't matter because we don't see the color, we just see the depth image. Here you can see again the goals in the first row versus what was achieved in the second row. And then here's an example with t-shirts, goals on the first row, achieved on the second row. So there's some errors, but it performs reasonably well, much better than previous approaches. So here you can see our comparison to previous approaches. On the x-axis is the inference time, and the y-axis is the accuracy. So lower is more accurate, and to the left is faster. And you can see that compared to other methods, we're much more accurate and faster. Qualitatively, here you can see our method will be achieved on the left versus the goals on the right. And here you can see what was achieved by one of the best performing previous methods. And you can see there's a clear qualitative difference between our performance and that of the baseline. This is obviously a simulation comparison, but this shows that the difference is not just in the numbers, but also qualitative as well. So to wrap up this part, we have a novel flow-based approach for bimanual goal condition cloth manipulation, in which we explicitly reason about the desired object motion and then infer the robot motion. And we, using this, are able to successfully perform cloth folding in the real world. Okay, so I think given the time, that's probably all the projects that I will have time to talk about, but you can feel free to ask me later about any of the other projects. But let's talk about the takeaways. I've talked about at the beginning that we're trying to bridge a gap between perception and planning. And how do we actually, what are some insights that we have gained from these projects about how to do that? So the first project at a very high level, you can think of as using a graph to reason about the relationship between object parts. And the second project you can think about as reasoning about explicitly about the relationship between the current state and the goal. And so both of these projects incorporate this idea of reasoning about relationships. I think relationships is something that's extremely important for many tasks, but it doesn't take a high enough priority in machine learning. So I think putting relationships as a first-class citizen in machine learning methods will greatly benefit our ability to achieve many tasks. Okay, so where are we going in the future? In the future, I'm interested in general in representation learning for deformable object manipulation. So how should we represent these different objects to achieve tasks, these different tasks? So some examples that we're hoping to look at are more in terms of clothing manipulation, also dough, mixtures of solids and liquids, other kinds of objects that you can fold, granular material, articulated objects, and other types of deformations like squeezing a lemon or peeling vegetables. So what does this involve? So one aspect that I'm interested in is reasoning about object interactions. So how do we reason about object-object interactions, object-tool interactions, or object environment interactions? These all involve reasoning about relationships, which is something I mentioned that we incorporated in our previous work. And there's other types of relationships that I'm hoping to explore as well, like those on this slide. Also, how do we reason about heterogeneous materials? So the projects that we talked about today were all cloth, which is an interesting material, but what if we have a mixture of different kinds of materials? Also, how do we perform long horizon reasoning for deformable object manipulation? There's many great works out there that already do long horizon reasoning, including for deformable object manipulation. I think there's other kinds of representations that we've been exploring. So it'd be interesting to think about how we can integrate those new representations with methods for long horizon reasoning. So hopefully I'll get to talk to Dimitri about some of these ideas later. Okay, so to summarize, these are the different projects that I showed at the beginning. We only talked about the first two, but if you're interested, you can ask me later about any of the others. So on the top right, we're learning how to slide along the edge of a cloth using tactile sensing. On the bottom left, we're learning how to grasp the edges and corners of cloth that's crumpled in different configurations. On the bottom center, we're learning how to grasp transparent and specular objects. And on the bottom right, we're learning how to pour transparent liquids into transparent cups. So yeah, feel free to ask me about any of these other projects later. And I'll also mention the terrific students who I worked with that led each of these projects, without whom none of this would have happened. Some other work that I also haven't talked about that you can please feel free to ask me later is in the area of self-supervised learning for autonomous driving. So a lot of autonomous driving these days relies on large labeled data sets, but really we can collect autonomous driving data faster than we can label it. So can we learn from unlabeled autonomous driving data? Here's a few papers that I've worked on self-supervised perception for autonomous driving for different kinds of tasks. These are mostly published in computer vision conferences. And we've also worked on a direction of active perception with light curtains, which is a new kind of sensor that requires you to choose where you want to sense. So this work was funded by Honda as well as the Argo AI Center and led by my fabulous students shown here. Sid Anka on the right is the one who led the active perception project, and he's also looking for postdocs. So look out for Sid as well. So finally, I'd like to acknowledge all the terrific students who I've worked with, as well as my generous sponsors. And I'll end here and take any remaining questions that you might have.